If you look closely at a major port, you see thousands of moving parts, colliding physical constraints, and massive operational friction. For decades, logistics providers have tried to manage this physical chaos using fragmented software. Dispatch, asset tracking, and accounting all operate in isolated data silos. Because these systems lack a shared state, a single delay at the terminal creates a cascade of misalignments across the supply chain, compounding data errors at every physical leg of the journey. To solve this, you have to rethink the software from the ground up. This is the premise of TMS 3.0. Before you can optimize physical operations, you must map them to a strictly deterministic software architecture. We call this bedrock the core cube. Instead of separate modules for operations, compliance, and billing, every action occurs on top of a single, unified structure. Physical movement and financial settlement are mathematically linked in real time. Once that rigid database is in place, it becomes the anchor for a safe layer of intelligent automation. We deploy a human-in-the-loop AI layer tethered directly to the core via secure REST APIs. You cannot deploy autonomous AI to orchestrate heavy logistics if the underlying data is shifting. The AI must sit on a flawless, single source of truth. Building that truth starts at the base layer, static master codes. In TMS 3.0, every truck, driver code, yard location, and customer billing rate is rigidly predefined and stored centrally. This master database drives a three-dimensional model. We have the front face for operations and settlement, the back face for resources and compliance, and the top face for business intelligence reporting. Let's look at what happens when a new delivery order arrives from a client. An operator inputs the order directly into the front face. Because of the core cube architecture, that single entry instantly populates the resource layer for dispatch and the BI layer for reporting. It entirely bypasses the need for manual duplicate entry. The financial calculations happen in the exact same millisecond. The system references the specific customer rate charts in the master codes and automatically triggers the accounts receivable pipeline. Concurrently, it calculates the expected operational costs. By pulling the cents per mile assigned to the specific driver and truck codes, it constructs the accounts payable pipeline. By locking operations and settlement together the moment a job enters the system, you eliminate downstream reconciliation errors. The single source of truth is established from step one. Looking closer at the front face, we see a shift in execution. Legacy dispatching relies on humans manually sorting tasks. TMS 3.0 relies on state-driven routing. The dispatch board operates as a digital Kanban workflow. Containers move dynamically across distinct operational columns, starting in a waiting list, shifting to the terminal, and ending at delivery. This movement is triggered by external APIs. When a vessel discharge signal, or DISC, is received from the port, the container packet automatically drops into the active waiting list. The physical journey is then broken down into job split legs. A single container's lifecycle is chopped into discrete data states, from port pickup to delivery to empty recovery and empty return. Each digital state change corresponds to moving real steel in the physical yard. When a driver hooks up to a chassis, they are executing one specific, targeted leg of that sequence. As the driver completes a leg, they log the status in their mobile app. That signal hits the master database, automatically migrating the container to the next dispatch tab without a dispatcher touching a keyboard. Removing the manual drag from routine container tracking allows operations to scale predictably, smoothly handling spikes in order volume without requiring a massive back-office expansion. With the deterministic foundation running smoothly, we can introduce Phase 2, AI orchestration. We overlay AI agents onto the core cube, communicating strictly through REST APIs. This setup enforces a hard security constraint. The AI agents are authorized to calculate and recommend, but they cannot write data back to the core system. Every execution requires explicit authorization from a human. Let's look at the AI dispatch module. This agent runs in a continuous loop, analyzing the entire pool of unassigned jobs against the current roster of available trucks and drivers. First, it pulls static variables from the master codes. It checks specific driver classifications, like whether they are a W-2 employee or an owner-operator, and calculates the exact operational costs based on their rate. Next, it injects dynamic telemetry. It pulls real-time Samsara GPS locations and checks the exact remaining hours of service compliance data for every driver on the road. The algorithm synthesizes all of this, location, cost, legal driving hours, and availability, to output the single most efficient driver-to-job match possible. That highly optimized match appears on screen as an approval prompt, waiting for the human dispatcher to review and validate it. This agentic loop shifts the role of the dispatcher. They are no longer doing manual data entry. They operate as high-level exception managers, applying human judgment to mathematically vetted options. We also need to extend that single source of truth outward to the client. The challenge is doing so without exposing the core operational database to heavy external web traffic. We solve this by spinning up a read replica database. The core cube pushes a one-way synchronization to this replica, isolating customer portal queries from internal systems. We then connect the Claude API using retrieval augmented generation. This rigidly restricts the AI's context so it can only ever read and reference that specific client's partition data. A client logs into the portal and uses natural language to ask about their container. The AI detects the intent of the question and queries the replica database to provide an instant, accurate answer. Behind the scenes, the AI tracking agent uses external Draydog APIs to continuously poll for terminal holds or last free day status changes. If the AI identifies an impending last free day threat that will incur storage fees, it acts autonomously. It emails the client, explains the terminal hold, and negotiates an alternative delivery slot. Once the client confirms the new schedule, the AI fires that mutually agreed-upon timestamp back through the REST API, updating the internal TMS dispatch board. By structurally isolating these external queries, we provide secure, automated client communication 24 hours a day, removing the risk of the AI accessing cross-company data. We now have a complete enclosed ecosystem. The core cube provides the foundation, the AI layer orchestrates the assets, and the API portals connect the outside world. But physical execution out in the real world is rarely perfect. That brings us to the final critical safeguard in the container lifecycle, the automated gross profit and payroll validation modules. This chart compares predicted and actual revenue. On the left, we see the expected gross profit. The system isolated this baseline metric the moment the delivery order was created, relying strictly on the static master codes. On the right is the actual gross profit. The AI calculates this dynamically using the finalized real-world execution telemetry, pulling from driver app logs, actual time on site, and Samsara GPS data. The AI validation agent continuously cross-references these two pipelines. It scans every completed job for microscopic variances, like a driver clocking slightly more mileage than expected, or a misapplied billing code. When the agent flags an anomaly that exceeds an acceptable financial tolerance, it pauses the settlement process. It generates a natural language explanation of the discrepancy and routes it to a human financial reviewer for a final decision. True AI utility in enterprise logistics does not mean removing human agency to run operations blindly. It means processing massive data pipelines to present flawless, mathematically validated options to the human in the loop.